That's the median. Okay, so we got the mean, the mode, the median. How do we get the standard deviation? It's a little more involved, but it's not terrible. I mean, first you have to, so basically remember, here I listed the data value. It's sorted already. You don't have to sort it with the standard deviation, but you can, of course. But essentially, you have to fill in the entries in this table, although it's already filled in. Okay? You know, you have to get the data value, each one, subtract the mean, square that difference as well. And here we have frequencies because we have a frequency table. Then you'll have to add up and divide by something. So the mean we got was 7, right? Okay, so we do, for each one, we subtract 7. So 1 minus 7, that's -6. 3 minus 7 is -4. 5 minus 7 is -2, and so on. You keep going. Square these differences, right? That's the next thing you do. That's what I'm trying to say here, right? So you have -6 squared, -4 squared, -2 squared, and so on. That's what we have here. And of course, then we have the frequencies, right? Because normally what you have to do is, since it's sample data, I'm not sure if I wrote that down in the, oh no, I did. Okay. Sample data, that means what you have to do is you add up all the squares and divide by n minus 1. N is how many data values there are. In this case, there's 53. So you would have to divide by 53 minus 1. Now, since we have the frequencies, though, instead of listing all the data, we just multiply by the frequency. So we have 36 times 11, 16 times 5, 4 times 3, 0 times 5, and so on. You add up all these products, and you divide by 52. And you end up getting this. Now, this is not quite the standard deviation, though. Here I went a little further out. So I probably should have deleted this, but that's okay. I mean, basically, you get that by rounding the 2 decimal places. The variance is this. But for the standard deviation, what do? Take a square root, like so. Take a square root, like so. Okay? So that's how we do it. And again, the standard deviation measures how spread out the data is. All right. So that's what we get here. Are there any questions about that?
Yes. Can you go back? How did you know that you had to like subtract 7? Or
7 is the mean. That's what we got.
Oh, okay.
On what is it? This slide.
Oh, okay. Okay.
Okay. You're welcome. Good question. Good question. Any other questions? Okay. So let's just, with probability, that's something else we had to do, right? I know we just saw this recently on the exam and stuff. I figured it wouldn't hurt to go through this. You know, if we're selecting R out of n items, right? And you want to make a listing, so to say. Well, if order matters, right? You know, if you change the order of the list you make, and by changing the order, you're getting different listings. Okay. Well, if there's no repetition, then you have a permutation. Okay. Then you have a permutation. If there are no repetitions, and that's what the permutation is. You know, I use Desmos to calculate this, so. But if there is repetition allowed in the list, so you can repeat a number, in other words, and again, it's just by the multiplication principle, which we've seen before, you get n to the r possible list. Okay. You know, you're making a list of size r, which is the same as choosing r items out of n possibilities. Okay. But if order does not matter, okay, that's where these combinations come into play, and that's what these are. Okay? So if order matters, permutation. If order doesn't matter, then combination. And that's, both of them are no repetition. So you can't use the same element more than once. And if you can, with replacement, you have n to the r. Not sure if there is a way to, I'm sure there is a way to handle the case when order doesn't matter, but you allow repetition. I just don't remember it off the top of my head. So anyway, here's an example. Suppose we're drawing 2 cards from a standard deck of cards, okay? What's the probability of drawing a king and then drawing an ace? Now notice here, right, well, yeah. I was going to say about order later, but notice the order does matter. We're drawing a king and then we're drawing an ace, right? That's implied from the problem. So the order does matter, in other words, because you want to get the king before the ace. Okay. Well, remember, this is what probability is by definition, right? It's how many favorable outcomes there are divided by the total number of outcomes. So in this case, it's how many ways we can choose a king and then an ace. That's our favorable outcomes, divided by how many ways can we choose 2 cards from the standard deck of cards where order does matter. Well, again, going back to this, order does matter, okay? So since order matters, we're going to have to use, and there's no repetition, right? Because we're not putting the cards back, so we have permutation. Okay? Right? We never said that we're drawing a card and then putting it back. So because of that, there's no repetition. So order matters, no repetition. This is what we use. Okay. So what are the favorable outcomes? Well, we know there are 4 kings in the deck, right? In a deck of cards. There's also 4 aces as well. Well, there's 4 ways of choosing the king. You're only drawing 1 king. So there's 4 ways that can happen. There's also 4 ways of drawing the ace. Okay, so there's 4 ways for the first outcome to occur. And there's 4 ways for the second outcome to occur. The total number of ways for both outcomes, you take the product. That's what the counting principle is. The multiplication principle, I think it's also called, if I remember correctly. In other words, you just multiply. So we have 4 times 4, which is 16. Does that make sense so far? If it doesn't, please say so and I'll explain it again. Okay, so there are 16 possible ways we can get a king and then an ace. Okay? All right, that's good. Now, how many ways can we draw 2 cards though, where order does matter, and there's no repetition? Well, as we said already, that's permutations. So that's this. So the probability then would be 16 divided by this, which turns out to be this here. Notice I didn't write out P of 52 in factorials. You don't have to do that. I mean, if you do, that's fine. I'm not going to take points off, but you don't have to do that. Okay. Good. All right. Are there any questions on this one? Here's another one then. Suppose 5 cards, they're drawn from a standard deck of cards. We're drawing 5 cards now. It's without replacement. Again, so again, that means no repetition essentially. In other words, when we take a card out, we're not putting it back. What's the probability then that all the cards are red? Well, so there's no repetition, but does order matter? Well, no, right? From the problem, all we care about is whether the 5 cards we draw are red cards. Now, to be red, what does that mean? That means it's either from the suit of hearts or from the suit of diamonds. That's what red cards are. Okay, well, how many outcomes are there, favorable ones? Well, remember, there's 13 hearts and 13 diamonds, right? We want the cards that are either diamonds or hearts, right? So there are 26 possible cards that we want, 26 possible red cards. How many ways can we choose 5 of those without repetition and without regard to, and where order doesn't matter? Well, that's the combinations, right? No repetition and order doesn't matter. That's combinations. Combinations. So there's 26 cards we can choose from. We're choosing 5. We get this. Okay, well, what about all the possible outcomes? Well, again, we're choosing 5 cards without replacement. And again, we're assuming order doesn't matter. Well, how many ways can that be done? C of 52, 5, 2. Not 2, excuse me, 5. That should be a 5. Actually, you know what? What the heck? Let me just fix it like this. That should be 5. Sorry about that. There we go. Okay. So in other words, what does that tell us? That tells us that, I had to delete that, the probability then is down here. So the probability then is down here, right? We have, this is the total, wait, hold on, let me get the laser. This is the total number of possible outcomes altogether. This is how many favorable ones there are. So we divide and we get this. You don't have to reduce such a fraction like this or any kind of fraction with probability. I mean, people generally don't reduce them. They don't write them in lowest terms. I mean, it's not wrong to, but I think by convention, people generally don't reduce it though. Are there any questions on this? So here's the next one, okay? This one's a little bit different, as you can see.